So the setting that motivates the constructions that we end up attacking is one that's kind of ubiquitous nowadays. It's cloud-hosted SQL databases. So here we have a client who has some sort of structured data, and they don't have the resources, or for whatever reason, they want to put this data onto some cloud provider service so that they can query it and perform their queries kind of remotely. And this is something that's offered obviously by tons of companies, probably more than there were yesterday. It's super popular. Unfortunately, there's this natural vulnerability that comes up, as I've drawn it here, is that the hackers who get into the cloud providers or insiders at those companies can just read the data off. And even if you do some sort of data at rest encryption, if you compromise the entire system and get that key, then you can still read that data. So a solution that has been proposed is called client-side or end-to-end encrypted solutions, where the client actually encrypts their data before they upload it to the cloud provider. And so this way, the cloud provider never sees the data in the clear, but the natural issue that comes up is that if a client wants to issue a query, the cloud provider has no idea how to process it, at least if you're just using standard encryption. And so there are tons of solutions out there for symmetric searchable encryption, maybe you've heard of that, where you have ciphertext with keywords and you want to index them so that you can search them, and that's all well and good and super useful. But if we care about SQL queries, then we need to support more than just searching over ciphertext. In particular, we need something like a queryable encrypted database. So it's the same setting as searchable symmetric encryption, but now the class of queries that we want to support is broader. So we want to do SQL selections, SQL joins. Ideally, we would have even more SQL operations, but that's kind of the limits of the state of the art without really heavyweight crypto. And so a type of framework that's been introduced for this is called structured encryption. And this has been, 2 decades running or something now, and this is basically generalizing searchable symmetric encryption, or SSE, where we just specify algorithms for setting up and generating query tokens and processing those query tokens with the encrypted data structures to support any class of queries, right? So you specify a class of queries when you specify whatever your construction is. So our work primarily targets 3 of these schemes, although it applies to many more other types of encrypted join schemes, and actually can apply to some of our attacks can apply to some searchable symmetric encryption schemes directly. But we focus in the setting of simple SQL queries. So we care about SQL selections and joins, and even within the selections and joins that we are concerned with, they're somewhat limited because that's all that the schemes support. Okay, so structured encryption is kind of nice in some ways because the security for structured encryption is proven with respect to a leakage profile. So formally, the view of an adversary can be simulated with this. If you don't know what a leakage profile is, it's intuitively just whatever the server learns while it's processing and reading or processing your queries. Right, so obviously we have to leak to the server how much data we have in our database. That's something that's very hard to hide in general. But there are also other types of leakage in some of these schemes. And some of them, it's not really clear how devastating it is. Right? I formally prove security with respect to a leakage profile, but the leakage is just a formal description of what the server is learning. Right? This isn't side channels. But it's not clear what the server could do with that information, at least a priori. And so a long line of work for over a decade now has been introducing leakage-abuse attacks. So this is trying to understand what you can learn from certain types of leakage. So the idea of a leakage-abuse attack at a really high level is that you consider realistic adversaries. Okay, so an adversary that doesn't just know the leakage. Maybe they know something else about the database. It's not always, and depending on the model, it's not always clear where the adversary gets it from, but you could imagine maybe there's some sort of hospital data and the adversary knows the frequency of certain diseases. And that would be an example of a distributional knowledge adversary. And so we can consider adversaries who get both the leakage as well as maybe some auxiliary data, and then try to recover something hidden, so something like the database or maybe the client's query activity. And so in our work, we actually consider this distributional setting that I just said, and we model it as the adversary has access to some previous year's database. All right? And so, unfortunately, I don't have a ton of time to go into the details of all of our attacks, but I will say that in our paper, we introduce 4 new leakage abuse attacks in this setting. And one of them is against SQL selection queries, or column equality leakage, which is present in all of these schemes that I've mentioned. And that's actually present in some searchable symmetric encryption schemes. So this is the one that can apply to some other prior work. We also provide 3 new attacks against SQL join queries. So when you perform a SQL join, something in the access pattern, what we call cross-column equality that I'll talk about a little bit later, gets leaked, and we provide attacks with using distributional information together with this cross-column equality to actually infer directly the plain text of the rows. And so in this talk, I'll just kind of give a flavor of this cross-column equality because it's kind of the new thing in our paper. It's a type of leakage that hasn't been attacked before our work. And I'll try to explain what cross-column equality leakage is and just go over some of our results at a very high level. So for those of you who have been like, what is SQL? I'm a cryptographer. Please remind me what a SQL join is. This is the slide for you. If you're watching a video, you can pause here. The idea is like, a SQL join is you specify 2 columns and 2 different tables. So I have a crimes table and a taxis table here. And the join output is just, I take wherever there's a row in one table and a row in another table, which match on the value, I'm going to concatenate those 2 rows and output it in the join output. Okay, so for example, the first row here gets matched, the first row in the taxis table gets matched with the first row in the crimes table. The second row in the taxis table also gets matched with the first row in the crimes table because they all have Bucktown, which is a Chicago neighborhood, if you're not familiar. And that's just what a join is. Technically, this is an inner equijoin for those of you who aren't cryptographers and actually know what that means. And the reason we consider this type of join is because that's all that these schemes support to date. And supporting like a more robust class of joins is actually a really interesting open problem. Anyway, so how the leakage comes up in these ST for SQL joins, I'll give a high-level overview of how a few of these schemes work. Basically, the client who wants to perform this join that I wrote on the previous slide generates a per query token. So this is just basically like a hash of the query they want to perform and some sort of key to open an encrypted multimap value. So then the server gets this token and uses the response revealing encrypted multimap to open the specific value. And this has the pre-processed query basically in it. So what resides in the encrypted multimap is just a bunch of pairs of row pointers, which are rows which match on the value, right? So these are just pointers to the encrypted rows, wherever the encrypted rows that should be combined and then output to the client. So this is exactly what the server needs to go ahead and compute the join without decrypting the rows. So it just goes and grabs those rows, concatenates them, and sends them back to the client. Okay? But what's leaked here is exactly what comes out of the encrypted multimap. In particular, it learns all of these pairs of rows which have matching values. And this is what we call cross-column equality in our work. So if we want to try to get an intuitive understanding of what gets leaked when I show you all of these rows, we can imagine an adversary who looks at the second row in the left table and notices that it matches with both of these 2 rows, and that's all it matches with in the table on the right. And so what they can infer is that actually the location in the second row is the same location as both of these pickups, as both the rows that it matches with in the pickup column. And it can do this with all the pairs, right? So then there's some underlying value which appears 3 times in the left and also 3 times in the right, and so on and so forth, right? So here are 2 other matches. And after it goes through all of these, we can basically, in our heads, imagine that it's just trying to figure out what these underlying unknown values are. So for example, this teal or light blue value was the first one that I drew. And it knows that there's some value there, which is the same on the left and on the right. And we can represent this just with a histogram or aligned histograms. So here we learn the frequencies of values, both in the left table and on the right table. Okay, and this is strictly more leakage than learning just the frequencies of values in the columns individually, because we're learning them at the same time, right? And so what we do in our work, specifically the attacks against joins, is that we give leakage abuse attacks using this histogram, right? So A leakage abuse attack is just an algorithm which takes as input this histogram, the leakage, together with some distributional information, which we, again, model as like a previous year's database. So we know like maybe Bucktown is just a more popular place to get picked up in a taxi than Lincoln Park, or something like that. And the adversary is going to use this distributional information to try to match up with the aligned histogram and guess what these unknown values are. And in particular, we give 3 attacks using kind of different algorithmic techniques that I unfortunately don't have time to get into to do these attacks, and then we test them. And so the way that we test them empirically is that we take some publicly available Chicago data. In particular, we look at crime data, crash data, taxi and rideshare table data, and then we run our attacks, right? So we simulate what would happen if you put these tables through a structured encryption for SQL scheme and observed the join. And you also had some prior year distributional information. We run the attack, and then we just calculate the percentage of values that you recover. So like in this example, I've recovered 2 out of the 3 values, and the percentage of rows that you recover. And what we find is that we can actually recover a substantial portion of the rows. So these are just 2 of the attacks we did. I would refer you to the paper to see all the different experiments we did. But even in our hardest case, which was the crime versus crash beat, what makes that hard is that there's a very big domain there. We still can recover more than 15% of both the values and the rows in most settings, or at least on average. And there are lots of other attacks. And it seems like this cross-column equality is really doing a lot of work compared to just the individual histograms, because we compare directly to attacks that only make use of the frequencies of the columns individually. And so I'll say just one more slide on our paper that we have other theoretical techniques that I really wish that I had time to go into. Like I said, we have 4 different attacks. Each is kind of using different algorithmic techniques that are interesting in their own right. Our SQL selection attack is actually generalizing a frequency analysis attack from prior work that was proposed against deterministic encryption. And then we provide a lot of proofs in our paper, and prove that they're actually like optimal inferences in like a Bayesian type model. And we actually show that some of the attacks are actually hard to infer optimally, NP hard, it turns out. And we give, kind of as an aside, we give an optimization algorithm for partitioning sets with respect to some objective function that comes up as like a sub-problem as one of these join inference types. And there are lots of other algorithmic ideas, and I would really encourage you to check out the paper if it sounds interesting at all. So that's all I'll say. I wish I had more time to go into the details, but thanks for listening.